least for the mix-up, I went and looked at the quiz, and I was like, this is not what the other class did at all. And I looked at it, I'm like, I printed the wrong thing. Way to go. I'm pretty annoyed at myself. Yeah. No, they had the right one. I have two versions, but I printed the wrong quiz entirely. Like it wasn't on the right stuff. So you could take a different quiz on different things than the things that I listed, but I feel like that's unfair too. Nobody wants to do that, even though it's like stuff you should know, but like probably not the same stuff you studied, which is... I would do that if I could leave you unattended, but I'm not allowed to do that. That's like outside of my job description. Just like, and then it's like, are we going to run out of time for somebody by the time somebody comes down here and gets the thing and comes back? And it's like, it's going to be too much. It's just I screwed this up. If I would have realized that an hour ago, I could have done something about it. But like a doofus, I just walked in and picked the thing up. It's like, that's not what you're supposed to be doing. All right. So chapter 13. This is, let's say conceptually, the hardest thing we do this semester. But that's a relative low bar though, right? Because has anything been really difficult so far this semester? Not really. And in practice, doing this, the calculator is going to do like all the heavy lifting for you. It's just kind of like understanding what I'm doing so that it's not just like blind button pushing. That makes it kind of like the hardest thing that we do this semester, but it's not even that hard. Okay, so just like take a deep breath. So what we're going to be doing in chapter 13 is mostly looking at hypothesis testing. So like if you do an experiment, how do you really know that something happened? And what you observe as a difference isn't just like random, right? That's an important thing to have to have evidence that like, hey, did something really actually happen when I did this experiment? Or is like the differences I'm seeing in my data just like random, right? Particularly if you're doing something that has like life or death effects on people. For example, what could be something that would have like life and death effects in an experiment setting? Medicine. Super important in medicine. We want to be incredibly diligent that like, did this stuff actually do anything or not? Like, is it actually killing people? Like, you don't want your medicine to do that. Is it actually making them get better? You'd like your medicine to do that. So we want to find a statistical way to kind of demonstrate that, yes, this is actually evidence that something is happening, either good or bad. Is everybody okay with that idea? All right, we'll look at a couple of different ways of doing that. Okay, so imagine you're trying to figure out how long on average it takes to install a new graphics card in a computer. The old graphic card installation took an average of 2 minutes. So this little symbol here, it looks like a U with an extra tail on it, is the lowercase Greek letter mu, mu. That's what this symbol is. We're going to use this symbol interchangeably with X bar to mean average. Everybody's okay with that? So it's just a new symbol. I don't know why we need a bunch of symbols that all mean the same thing, but when you have mathematics, it's like consolidated from different traditions that are done in different languages. You have a lot of symbol transition that nobody's willing to give up. And we had a standard deviation for that installation of 0.2 minutes. Remember, that is the lowercase Greek letter sigma. That's what this is. That's our symbol for standard deviation. We saw that already, right? That's what comes out of your calculator. So with the new graphic card, you believe that the new mean time is going to be 2.2 minutes to install. When testing your new installation times, you want to know if there is a reasonable chance of getting a sample with an average of 0.2 minutes. This would be considered a sampling error. This means that even if the sample were picked correctly, there still is a chance your randomly picked sample is a bad one. So what you might do is you might go and look back over your old installation times to determine the likelihood of getting a mean of greater than 2.2, given that the old card had a mean of 2 minutes with that standard deviation of 0.2. So how likely is it that the installation time for this new card is really the same as the old card? Right? Was it just like a random chance that we got a bad sample and really there's no difference in the installation times? Right? That's what we're trying to figure out here. So what is the idea then? So this graph here represents the distribution of installation times. So the middle of this distribution is the mean. We'll talk more about this shape of distribution later, but it's called a normal distribution. But the mean is here at 2. And I want to look at the percent of samples that I could take from this distribution that have a value of 2.2 or higher. So I'm looking at that region there. Is everybody okay with that idea? Now, the area under the curve is going to represent the probability that I get a sample that has an average of 2.2 or worse. So we're told here that probability is 7.6 times 10 to the negative 24. Is that a good chance or bad chance? Bad chance I get a sample of with an average of 2.2 or worse, right? Does everybody kind of see that? What would that tell me then? It would tell me that probably if I got a new sample that averaged 2.2, that's really different, right? Because it's pretty rare that I could have randomly picked a sample that had that bad of a mean. Do you guys kind of see what we're saying here? We haven't talked about at all how to do any of these things. We're just talking like conceptually, what is the idea behind what we're about to formalize, okay? We'll get down to like the nitty-gritty of like how. We're not dealing with how, it's just kind of like the why of what we're about to do. Is that okay? All right, so let's see, we read this. The graph above represents all the distribution showing a mean time with mu2 and a standard deviation of that. So that's our graph. According to the graph, there's this little tiny percent chance of getting a sample from the old installations that has a mean time of 2.2 or higher. So this means there's basically just like a 0% chance that a randomly picked sample is just a bad sample, right? It's that 2.2 mean is like different enough to say that, okay, this is really a slower installation. So that means that since it's really unlikely that the random sample we could pick would have an installation average of 2.2, we're pretty confident that this sample shows that the new cards have a longer installation time than the old ones. Does everybody feel okay with the conclusion if we talk through it? Okay. So in general, in this chapter, we're going to be looking at the relationship really between two variables. I don't want to say that. Look at variables and determine how they're related to one another. So we start with two hypotheses, or hypotheses. Okay? We have a null hypothesis. That's the thing we want to prove. So in the previous example, that might be that that there's no difference in installation time. Okay? So we're always starting with the assumption that that hypothesis is true. Our analysis then will either support or reject this hypothesis. So we abbreviate the null hypothesis with H0. So that means in the previous example that we would say the mean time is 2 minutes. That basically the two installation times are the same. Everybody's okay with that idea? The second hypothesis is called the alternative hypothesis. Typically we abbreviate that HA, although in some texts we use H1. This is the notation that I'm going to use. And this is the opposite of what you're trying to prove in the null hypothesis. Notice I say opposite. So it doesn't mean that the new mean is 2.2. It means that it's not 2. Everybody's okay with that? So simply stated, we want to show what will be true if we reject the null. Keep in mind that you can't prove a negative. So the alternative hypothesis just allows the data. That doesn't mean anything. So we don't ever reject this hypothesis. We just would accept the null as correct, or we would reject the null as false, supporting the alternative, right? We never reject the alternative. It's either we support the null, done, or reject the null in support of the alternative. Is that okay with you guys? It's like, it's like the idea of you can't prove a negative, like prove Santa Claus isn't real. Right? Like, how do you do that? Prove Bigfoot doesn't exist. How do you do that? You check everywhere? How are you going to do that? You can't really, because as soon as you've checked one place and left, maybe Bigfoot just moved to that place that you were occupying before. Like maybe he's always just one step behind you. You can't really prove something doesn't exist, right? Does everybody feel okay? Okay. So in our last example, our alternative could be something like the mean time is greater than 2. Now, sometimes we'll say not 2, and in some of the, depending on the test, we might give the, say, okay, it's bigger or it's less or it's, so depending on the test, that may change. And that's what I said here. Note this is not the exact opposite of the null. The null would be, or the exact opposite is just the mean isn't 2, which means it could be higher, it could be lower. We'll look at different ways of doing it when it's just like not lower or higher in a minute. So again, we haven't talked about at all how to do this testing. We just said, okay, we're going to set it up as like the two things are the same. The alternative is that they're different. We're going to do some analysis that's either going to say, okay, yes, this is our data is in support of them being the same, or no, our data, contradicts them being the same, which is evidence for them being different. It doesn't prove that they're different. It just, is in support of. Does that feel okay? So we're going to be picky about our verbiage, right? Reject and support. All right. Okay. So one way that we can do this is with what's called a t-test. Now there's a couple of versions of t-tests we're going to look at. This first version we're going to look at is a one sample t-test. Any of you guys in we have a bunch of IB. Anybody's in IB biology, and have we done t-tests in biology on experiments? No. Okay. Sometimes that happens. Or AP Psych, have you talked about that? Yes? Cool. So you're one step ahead. Maybe. Okay. Super common statistical test if you're doing any kind of experiment. All right, so we're going to look at an example. This example came from the textbook. It says a factory produces light bulbs that are known to last 8,000 hours on average. A new type of light bulb has been developed by engineers, and they claim that it lasts more than 8,000 hours. Management's concerned that the cost of producing the new type is more expensive than the traditional method. They can justify changing to the new process if they have evidence the new light bulbs have a longer life than 8,000 hours. To try to show this, we've taken a random sample of 25 light bulbs, and we found that those 25 have an average life of 8,600 hours with a standard deviation of 1,000 hours. Okay? So we have this new light bulb that we've designed. We think it's better. So we sampled 25 from this pool of new light bulbs and tested them. The average lifespan was 8,600 hours, and the standard deviation of lifespan was 1,000 hours. We want to know, is that new light bulb really different, have a different lifespan than the old one? Or did we just pick a weird sample? Is everybody okay with that idea? Okay. So the question is that enough evidence to justify the two light bulbs really being different? And in turn, changing the production design of our factory. Yes, sir. Sure, you're going to miss the good parts, though. It's okay. I understand. You got to go. I'm just letting you know. Okay. What we're essentially asking is, what is the likelihood that a sample of 25 light bulbs with a mean of 8,600 hours could have just been picked from the old light bulbs that had a lifespan of 8,600 or 8,000 hours, right? How likely is it, could I have just taken 25 of the old light bulbs and gotten the same lifespan, the same average lifespan? That's what we're going to check. If that probability is high, then I don't think there's a difference. If that probability is low, then it seems like these two light bulbs are really different. Is everybody on board? Okay, so let's start by setting things up. So our known data, the mean for our light bulbs is 8,000. So I'll say mu naught equals 8,000. So that's like the mu null. Like the null hypothesis is the light bulbs have an average lifespan of 8,000 hours. My new mean, my alternative, or my mu A, or I'll write it as x bar in this example, is 8,600. That's the mean for my sample. And the standard deviation from the sample, so like my SA would be 1,000 hours, or you could do sigma A, right? Because sigma is also the notation we use for standard deviation. And now we're going to start by writing out our hypothesis. So we're going to write down our null and alternative hypotheses. Everybody's cool? Okay. So our null hypothesis is just that the average lifespan for the light bulbs is 8,000 hours. So I can just write mu equals 8,000. Everybody's okay with that? That's the real average. The alternative is the opposite. But what are we actually trying to show? Is that the new light bulb average is greater than 8,000. So I'll say my alternative is mu is greater than 8,000. Right? Many times that alternative is what we're actually trying to show, right? We always just start by assuming, though, that there's no difference, really. So far, so good? And again, you can just write your null and alternatives in symbols. You don't have to write in words, although it's correct to write it in words as well. Is everybody still on board? Still okay? Okay. Now we're going to do the calculation to find that probability. So this is called a one-sample t-test on your IB exam, on my test in this class. You are not required to perform one of these by hand. All you need to be able to do is to have the calculator do it for you. That's what we're going to show you now on how to do it with the calculator. Deal? Sounds good, Mr. Kulik. You will, however, be expected to interpret the results. So based on what the calculator outputs, you should be able to say whether we accept or reject and all that jazz. We'll talk about how to do that. So we're going to start by opening up our calculator. If you have your calculator with you, I welcome you to follow along. You're going to start by pressing the Stat button. So your screen should look like this. We'll move over to the Tests tab. And then you're going to pick option 2, which says t-test. Everybody still doing good? Okay. From there, our null hypothesis, or our null mean, was 8,000. Our new mean is 8,600. Our sample standard deviation was 1,000. We took 25 samples, and we want to show that our new mean is greater than the null. So that's how you start by setting it up. Is everybody okay? The number of samples. So we said we sampled 25 light bulbs in the problem. So it's just the size of your sample. We just plug the numbers in. And then we'll hit calculate. And blammo, this is what outputs. What's the thing that we care about here? We care about the P. What is the P? Probability. Close. A percentage is a probability, but to get a percentage out of this, you'd have to multiply it by 100. So it'd be like a 0.3% chance that we picked this sample with an 8,600 mean from light bulbs whose average lifespan is 8,000. Is that a good chance or a bad chance that we picked that? Pretty bad chance that we picked a sample with that high of a mean, right? So if you hit the draw option, you get this. You can't really see much because it's just like something over here is shaded in. If it was a big probability, you'd be able to see like the piece that it shaded. You know what I mean? Okay. Yes, sir. Did you pick the t-test?
Yeah.
What's going on, Joey, now? Oh, why? Because we want to show that the new mean is greater than the old mean, right? So we want to show that our new mean, that's the mu, is greater than our null, which we said was 8,000, right? So it's basically just wanting to make this statement. Does that feel okay? Okay. All right. So we did that. So the two numbers we have are this t equals 3 and this p. The t is what's called a critical number, and it basically tells us how far away from the mean our distribution is from the original mean. So basically, this is saying that this mean of 8,600 is like 3 steps away. 1, 2, 3 from the old mean. Okay? Now, that number's not very helpful just by itself. What we really care about is the p, which basically says that we have a 0.3% chance of having picked this sample from light bulbs with lifespan of 8,000 hours, which is pretty lousy, right? Yes, Sam?
Is there like an objective probability that's
This is exactly where we're heading. Yes. So Sam's asking, like, okay, so 0.3 is obviously low, but like, where's the line at, like, okay, it needs to be less than this or greater than this. What's that line at? Right? That is exactly the next question. That's exactly where we're heading. So just sit on that for one moment. We're going to get there. But that is exactly the question you should be thinking. Like, okay, that's low, but how low is low enough? Right? Everybody kind of get what we're saying? Cool. All right, so we have that. We said all this. So what we would say here is, because this probability is so low, it's in support of our sample being really different from the original. So we'd reject the null in support of the alternative. Okay? So you would say we reject our null hypothesis in support of the alternative, meaning that these new light bulbs we've created actually do last for more than 8,000 hours on average. Yes? Sure. Is everybody okay with that idea? So let's look at what would have happened, say, if instead when we did our sampling, our average was just 8,200 hours. So the exact same setup as before. You know, the average of the old light bulbs was 8,000. We sampled 25 of them. The new average for that sample was 8,200. The standard deviation was still 1,000. What would have happened if we did our t-test then? So we'd have the same exact setup. We do this, and what's our probability? 1.6, right? So a piece of vocab here. When we do this kind of t-test where we're looking at, is it greater than the mean? We're looking for like this part of our probability. That's called an upper tail, because we're looking at like the upper greater than. So if we're looking at if the alternative is greater than the null, that's an upper tail. What would we think it would be called if it's the alternative is less than the null? What if we're looking at just not equal to the null? Two-tailed, because you're looking at both ends. right? You can have stuff that's small and stuff that's big, but not right at the mean. So that's just a piece of vocab, that this type of t-test was a two-tailed t-test. Now, if we look at this one, this probability, 16%, is a lot higher than the last one of 0.3, right? Do you think that's high enough that we would accept the null? Maybe. Typically, what we end up doing is, in the problem, we did this. We talked about, okay, so this is just talking about lower tail, blah, blah, blah. Here's two tail, blah, 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 right? So this is the setup for a two tail. So if I look at these previous four tests, this is our upper tail. This was also an upper tail. This was the lower tail. And then this one was the two-tailed. Now this is so close to zero, that's obviously going to be enough to reject our null. But what about these other ones? 80% seems real bad, right? Yeah, you can probably look at that and be like, okay, that's way too high. That's likely that the null is correct. We'll accept the null there. That's super obvious. What about these other two, though, 16 and 32? Are either those low enough or high enough that we would either, reject or accept the null? And what is small enough or big enough, right? When it's super big and super small, it seems obvious. Yes, sir. Sure. So, what do we compare this p-value to? We compare it to a level of significance. So in statistics, we abbreviate the level of significance with the letter alpha. And that level of significance is basically saying, okay, what's the boundary? Like, how bad of a sample do we have to get? Or before we say, okay, that's now not just like a unlucky sample. That one is like really different. Yes?
Oh, sorry, this is kind of a older sample. What is like a two-tailed test?
So this one where we looked at not equal to 8,000 is a two-tail, because you could have the stuff that's less than 8,000 or stuff greater than 8,000. So you're looking at both ends of that probability. Does that make sense? Okay. Okay. So in practice, for us, that level of significance will be given to you in the problem. So it'll just say, like at a 3% level of significance, should you blah, 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 blah. Right? We gave you the information about the light bulbs, and it would say at a 3% level of significance, should we, or 5%, or 7%, or 10%, or whatever percent gave you, should we, switch to that new manufacturing? So if I compare our old ones to any of those previous examples, 16 and 32, those are way bigger than the usuals, right? So we'd probably be accepting the null on each of those, because the odds are pretty decent that I just got, a weird sample from the null. Everybody's okay with that idea? Okay. So basically you're comparing your p-value to the level of significance. If the p-value is less, that means that there's a small chance you could have gotten that sample from the like the old stuff. So you'd want to reject that the old stuff is correct and accept or support your alternative, your new. If the P is bigger than the level of significance, then you'd accept your null, saying that, yeah, the old stuff is still the same as the old stuff. Is that okay with you guys? That's a rule that you will want to have memorized on when to accept or reject based on your P and alpha. Okay.
So less than, it's like really like slim chance.
Less than means that you should reject the null. Greater than, it means you accept the null. Because less than means there's a slim chance you could have gotten this sample out of the old stuff. Okay, everybody's good on that? Now, I'm going to warn you that you really got to have that memorized. You can't screw that up. Okay? All right. Okay. So this is just what I'm saying. So if the probability is greater than or equal to the level of significance, we accept the null. Otherwise, we reject. Right? I guess I didn't include the greater than or equal to. I just said greater than. But equal lands on the null side. And if it's a hard less than, we reject the null and support the alternative. So here's your summary page. So notice here that I have accept and reject, right? The accept word, saying reject is great. That's fine. No issues there. Saying accept, because you haven't actually proven anything, right? You've just found evidence in support of. So we want to be careful about using that word accept. Rather than saying accept, you could say fail to reject, or you could say evidence in support of. What's up? Oh, really? Maybe I was right when we were saying. Okay. Maybe you're warming up to it. A what? SEM? Okay. Yeah. Sure. Okay. Everybody still good? There's lots of different hypothesis tests. We're going to look at two. We're going to do t-test and then what's called a chi-square test. Everybody feel okay on this? So the verbiage, the takeaway is no bueno on accept, right? Fail to reject or evidence in support of instead. So what I want to talk about next are called type 1 and type 2 errors. Remember, this is just a probability that we're looking at, right? So there is still a chance that you even though the probability was like 0.3%, that you could have picked this sample from the old light bulbs. That ain't zero. What do we say if, like, for example, we just got the unlucky? So let's look at this illustration. So we have the true outcome. So either the null was true or the alternative is true. And then we have the decision that we made from our statistics. Either we did not reject the null or we rejected the null, right? So if the null is true and we did not reject it, everything is fine, right? Or if the alternative is true and we rejected the null, everything is fine. No error was made. Right? Everybody's cool? Now, what happens if we did not reject the null, but actually the alternative was the true result? Oh, I did the wrong one first. What if we rejected the null, but the null was actually the true result? That's called a type 1 error. So that's where you think something is different, but they are actually the same. Right? So thinking about medicine, right? Like if you're doing like a COVID test, that would be you got a positive result for the COVID test when really you didn't have COVID. Right? The test said it was you were different, but it was really the same. That's a type 1 error. Is that worse, better, or worse for public policy standpoint? I'd probably rather make a type 1 error than the alternative, which is where it's actually different, but we said it's the same. That'd be like you taking the COVID test and it coming back, you're not sick, when really you are sick. That's the one that you want to watch out for. Everybody's cool with that idea? That's the type 2 error. So if it's like a disease screen, you'd rather have false positives than false negatives. Right? So you guys are aware that in most professional sports settings, specifically like in a lot of the Olympic sports, they do out of competition and in competition drug testing, right? One of the ways that you can reduce the possibility of getting a type 1 or type 2 error, which would be like I tested you for this performance enhancing drug and it came back positive, but really you didn't take anything. You got a false positive on that. Is to take your original sample and split it into 2 and always repeat on the positive to make sure you got another actual difference, right? That will help eliminate like a type 1 error, is to do a second screening and make sure you get another positive result. So like oftentimes in testing, you want to find or design a protocol to try to mitigate these type 1 and type 2 errors. Now, is it possible that the second result also comes back positive, even though you didn't take anything? It's a non-zero probability, but it's certainly way less because it's multiplicative, right? It's like this probability times this probability would be the result of getting both of them coming back false positive, which is pretty darn low. It's basically like you're getting hit by lightning low or winning the Powerball, but not zero. You guys feel okay with this idea of these type 1 and type 2 errors? It's basically the false positive and false negative, right? Most cases we shoot for the false positive and we really don't want the false negatives, right? You don't want to find out later that they said, oh, you weren't sick, and then you actually really were very sick and you need to be treated and you didn't do anything. Although treating someone who is not sick can have, ramifications also. Like you're probably better off not taking any medicines than taking medicine you don't need, because all medicine is basically just poison. It's a dosage question, right? You take enough of anything, it'll kill you. Or it's not great for you. Let's say that at least. Even water, right? You drink too much water, it'll kill you. Well, you screw up your electrolytes and then your heart stops because you can't keep your heart beating because you've diluted your... Anyways, this is beyond. Anyways, going on. All right. There's another type of t-test called a pooled t-test. Let's look at that. So this is another example from the textbook. It says a comparison of the amount of nicotine that could be inhaled from cigarettes of the same brand differs between countries. There is some suspicion that local cigarette companies boosted their cigarettes' nicotine content to maintain or even increase present addiction levels. A study of 40 randomly chosen cigarettes was conducted to investigate this issue between 2 European countries. The recorded average level of nicotine in cigarettes in both countries is given below. So country A had an average of 0.85 and country B had an average of 0.30 with respective standard deviations of 0.2 and 0.18. And we want to know, is that evidence that the nicotine level in these 2 countries is really different? Or could this just be like unlucky samples is why we see the difference here? Right? So this is very common, like hypothesis testing, right? You have your control and your experimental. You want to find out, are these 2 things, did anything really happen here? Is there anything really different going on? Pooled t-test. Everybody's cool? The regular t-test, you would have tested against a known standard, right? Here, you're doing like an experiment, like control versus experimental. Everybody's okay with that idea? So this is a mu, that's average. That's a sigma, that's standard deviation. And we're going to do that testing at the 5% level of significance. Okay, so let's show you how to do this. So I've just recorded or written down that information that it gave to me. So this is a different kind of t-test. In the previous example, we had a single random sample against a known distribution. That's why it's called a one-sample t-test. In this one, we want to compare 2 different distributions. This is called a 2-sample t-test. And just like before, you don't have to do any of this by hand. You just have to know how to set it up on your calculator and interpret the result. Okay? Let's handle that setup. So, start by writing out your hypotheses. So, your null hypothesis should be that mu A is equal to mu B. Or you could write it as the difference is equal to 0. They're equivalent forms. The alternative is that they're different. So we just say that they're not equal to each other. Or you could say the difference is not 0. Everybody's okay with that? Okay. Now, calculator time. So stat. Go over to tests. This time we pick the 2-sample t-test. So it asks for mean 1, standard deviation 1, number of samples. Mean 2, standard deviation 2, number of samples. And then we want the alternative hypothesis here, which is that they are not equal. So we had 85.2. It told us that we took 40 cigarettes in the question. That's where the n came from. It was in the question. We didn't. I guess I should have put it up here in the written down stuff from the previous. But in the question, it said we sampled 40 cigarettes. Now the question is here, the pooled. That's new for us, right? In IB land, always pooled. Pooled is always yes. Make a note of that for yourself. It's easy to forget, but pooled is always yes. What's up, Joey?
Can't see.
You needed to pick a better seat than all the way in the back.
Why?
Yeah, what's up, Grace?
What is SX?
So SX is the standard deviation for the first thing. So that was 0.2. And then SX2 would be the standard deviation from the second sample. What's up? Okay. Are you on data or stats? Show me your calculator. Yeah, it's just a weird different order. I don't know. I think it's fine. The standard deviations. Okay. If we hit calculate and draw, so here's our calculate. That's the output I got. And there's my draw. It's just a two-tailed result. You just can't see the shading because look at the probability. Very, very small. Well, it's 9.9 times 10 to the negative 17.
Really small.
Very small, right? So, if we compare that to our 5% level of significance, we would say we reject the null. These are actually different. Correct. No.
It's smaller.
Well, what we have to be careful what we're saying it. If the probability is less than the level of significance, we reject the null.
So it's bigger to be accepted.
Times 10 to the negative 17. So, way less. So what is this telling us? The cigarette company's playing with their goosing their product there a little bit in one of these countries versus the other, right? It's saying, is there difference between the two, right? So we can say definitively there is difference.
Wait, so how do you know they're using it? Like, how do you know?
Well, because one mean was 0.85, the other is 0.13. In the different countries, they're doing something different in one country than the other. You're getting much more nicotine on average in one country than you are the other.
And so what are you measuring?
You're measuring the probability that even though these things are, you're measuring the probability that if all these cigarettes were really the same, could have I sampled 40 and 40 and gotten the means that from my sample that I got? What's the probability of me being able to do that? The probability is this 16 zeros and then a 99. So it's basically you're getting struck by lightning if you're able to pull that sample out of there. It's almost impossible that you would have been able to do that. There must be some difference between the cigarettes in country A and the cigarettes in country B. So they're messing with the recipe somehow or the manufacturing somehow that you're getting more nicotine in one country than the other. Alessa.
So is it basically seeing if you repeat it,
It's basically saying, what if all these cigarettes are really the same? Could I have drawn a sample from that and gotten these kind of means out of it? And here we're saying no, it's very unlikely you'd be able to do that.
Does this data show us which country is messing?
It doesn't tell you which country it's messing. Although you can I would say that we can say that country B has more nicotine on average than country A. I don't know why you'd be decreasing the nicotine in your cigarettes more than you would, than like the limit that is set by the country, because you want the people to smoke as many cigarettes as you possibly can. Actually, maybe not. Maybe that'd kill them too fast. But you get the idea that like you want probably more nicotine than less in your cigarettes if you're a cigarette company. Not if you're a consumer. Maybe you do if you're a consumer. I don't know. Maybe you're like, I just need that. Need my cigarettes. Give me that nicotine. I'm smoking with the patch on anyways. It's fine, you know? While chewing a piece of the gum. It's like, give me all the nicotine. I don't know. All right. And again, so we say that there's enough evidence to conclude that there's a difference. All right, let's do another example. Where are we at here? Oh my God, stop.
We have
How much time do I have here? 20 minutes?
15 minutes.
Okay. What's up?
So for the last one, that would then support the alternative?
Correct. Yep. Correct. Actually, we're going to stop here before I get into this example. I want to talk a little bit about some IA stuff. So if you recall, this being an IB class and all, we have to do this internal assessment. This is like the major project for this first semester. The culminating item that you're going to produce for this IA is going to be a paper. That paper is going to count as your exam grade for first semester. The typical due date is that week you're coming back from Thanksgiving break.
So is that
There is no in-class final exam. Yeah, I know. I figured that's a decent trade, right? All right. So let's talk about what you're going to be doing, because we're going to start doing some work on this here soon. So you're going to choose two quantitative variables. Remember, quantitative means it's a number.
numbers?
And try to determine if the two variables have a cause and effect relationship on one another. The variables you're going to choose are entirely up to you, but they must be something we can use in a calculation, hence quantitative. The relationship that you're choosing should be unique. That means that no two students can be looking at the same two variables for the same relationship. So for example, you could say, look at how much sleep somebody gets versus their GPA, or their GPA versus their overall ACT score. Okay? Now, those two are not topics that I would approve, because they're topics I'm presenting to you as an example. And you're encouraged to be inventive. They don't have to be school related, but you should think about the data collection side of this. So regardless of what you're doing, you're going to have to collect some data on these two quantities that you want to, or these two variables you want to compare. So if you choose to do something, you can collect data via survey. I can help you get survey responses from fellow seniors. Or some students will find like a database available to them on the internet and collect their sample from an already available database. For example, I think Isaac Kanja last year looked at the relationship between running speed and stolen bases in MLB players for the whatever that season was, the 23 season. You could do something like that where you can collect data from a source. Now you have to find the database and you have to collect a sample from that database. Or you can collect a sample via survey. Either are acceptable. But as you're thinking about what you want to do, definitely think about the collection standpoint and how you would do that. I think one year somebody wanted to do like, the amount of sunlight a plant gets and then how far it grows. And I was like, what data? How are you going to collect this data? Like you're going to plant like 70 plants and, like record their heights in sunshine and every day. And they're like, no, never mind. I'll do something different. I'm like, okay, that's fine. It's just like, you have to collect this data. That's a wonderful idea. Be super interesting, but not super, really time consuming and difficult from a data collection standpoint. Okay. So then, we're going to collect some data. We'll do some statistics on it, write about what we did and what we found. To do this, to help you guys get through to the end, we're going to have certain milestones along the way that you're going to do for turn into me for like quiz points. So the first one is to get a topic approved. So that's a 20-point quiz assignment. The topics will be on a first come, first serve basis. So like the first person that submits their topic and gets, with that idea and gets approval, they get a shot even if the next person wanted to do the same thing. So my suggestion to you, to be on the safe side, is submit for multiple topics. Because if I reject the first one, I'll go to the second one. And if I just reject the first one, send it back to you, now maybe 20 people have gotten in line and taken your second choice before you even had a chance to present it. Everybody's okay with that idea? So your submission should look something like the following. It needs to include 3 things. So you need to have a clearly stated independent and dependent variable. Remember, the independent variable is the cause. The dependent variable is the effect. Then you need to say what you're trying to show. Like I will try to show the number of hours of sleep a person gets per night impacts their overall weighted GPA. I hope to prove that the more sleep a person gets per night, the increase in their overall GPA. Great. Like a couple of sentences telling me like what you're doing or what you're trying to show and what you hope to prove. And then I want like about a paragraph, like several sentences about why this topic is important to you. So notice this topic is important to me because, and then I leave it to you guys to kind of fill in the because. Is everybody okay with that idea? One paragraph. Not like a page, a paragraph. And it could be that, like, oh, I'm a senior and like I'm trying to get into this good school. I know my GPA really matters. I'm trying to find ways to maximize my GPA. And I want to find out if I should spend more time studying and sacrificing sleep, or if I should try to get more sleep and maybe sacrifice a little bit of studying. Which one would help, is going to help me, like maximize my GPA so I can get into this really good school I'm trying to get into, or something like that. Like that would be a reasonable why this is important to you. Okay. Or you could have a why is this important to you from like a holistic standpoint. Like if you're looking at, poverty levels versus like, like tax spending or something for counties, you can make an argument that like as a nation, as a society, we want to, like decrease poverty in general. I want to look at, if like tax spending actually has significant effect in poverty, blah, 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 something like that, where it's clear that this affects everybody, and you could tie in that maybe you're interested in a career in, politics and civil service, and you want to, like make good data-driven decisions, and you can elaborate in a way that like connects it back to you, why this is important to you, even though it's like clearly should be important to kind of all of us as humans. Does that feel okay? So that's the first milestone. I'll show you the submission details here in a second. Your second milestone is going to be your data collection. So whether you collect that data via database, like you find a source on the internet, or you're using a survey, turning in your data to me will be your next step. If you're making a survey, we're going to make Google Forms because it just makes life a million times easier because you don't have to do any data entry. You just like, get the numbers into a spreadsheet and you're basically done. You do need to make like a two-way table. And now when it's time to write these surveys, we'll talk about like things to do and not to do in the authoring of your survey. The next milestone is writing your introduction, turning that in. And I'll talk more about like what your introduction should include and not include and what that'll look like when it gets closer. The fourth milestone is doing your calculations. So once we have our raw data, we'll take a day in class. We'll do all of our calculations in an Excel sheet. I'll check your calculations to make sure you haven't goobered anything. That's the next milestone. And then the final is the final write-up for what you've done. So we're going to do a lot of this along the way in class. Basically, everything you'll need will be done for you. You just need to write about what you did and what you found. But the calculations should be done and checked. The data collection will be done and checked. The introduction will be done and checked. You'll have a lot of it taken care of before you get to the end. And then this talks about what are the different sections you should have and what should be included in there. I'm not going to go through that right now because it doesn't matter. If I look at this piece here, this fourth one in the I-8 column, this is the instructions for the submission. So you want to email it to me. Your subject line, everybody listen, the subject line in your email must have this format. So it would be period 3, IB Math SLIA dash part 1. If you don't have that subject line, I'm going to reject it and just send you an email. I've rejected this because you have the wrong subject line. You should attach to it a Word document or Google Doc link. I don't want it written in the body of the email. Everybody's okay with that? Your Google Doc or Word, or your Google Doc also needs to have the permissions on it. If I can't read it, I'm going to reject it because I can't read it because your permissions are wrong, and you can try to resubmit it, but maybe somebody will beat you to that topic before you can get it back, before I get back to you, because you go to the bottom of the email queue. And then if you're giving me multiple topics, rank them, 1, 2, 3, first choice, second choice, third choice, or whatever, so I know which one to give you. And then the deductions that I would give you for lateness or missing info or whatever. Everybody's cool? Okay, so this is in the content library here. It's the fourth option. I've also, I can't show you, on My Notre Dame, there's an announcement on there. If you click on the announcement and look at it, there's a link. There's a bunch of words. Basically, the words are just, it's just this paragraph again. But at the bottom, there's also a link to click on that takes you to the Google Doc of people's accepted topics. So if you're looking at that and be like, I wonder if somebody's already chosen this, you can check. Or if you're like, I don't have any idea what to do. What's other people doing? You can maybe get an idea. Any questions about this? Okay. I am now open for submissions as of right now. So you can start emailing me submissions as soon as you can think of one. Listen. Let's make a soft due date by our first class day next week, so Thursday or whatever. Soft due date. Okay? As long as you've gotten something in, you miss the late points deduction, even if I reject what you did. That'll give you on timeness. Everybody's cool?
So it's just the email that's due on Thursday.
Yeah.
Email due Thursday.
Yeah. Make sure you read the submission criteria, though. Okay? Everybody's cool? All right. I'm done talking.